Hello everyone, I'm a technical support engineer from SuperMap. Today's session we will have an introduction on 3D data processing in SuperMap iDesktop. So here, for 3D data, it will be displayed as a scene node in the Workspace Manager. The scenes node in the Workspace Manager manage all the scenes in the workspace. A scene node is a model of the Earth with a globe overlaid with world image. Geographic features on the Earth's surface can be simulated on the globe. Scene can facilitate the understanding of the location of geographic features and the relationship among them. And you can add 2D and also 3D data to a scene for browsing and some other basic operation. A scene also models the environment of the Earth, including the sky, the atmosphere, the fog, and other things. And besides, you can also observe the globe from different perspectives through the camera settings. Scenes rely in the scenes window. There is one-to-one relationship between scene and scene window, and a scene cannot exist independent of a workspace. Therefore, you must save the workspace on which a scene relies if you want to save the scene in the future use. How to load a scene? You need to right click on the scenes node and click new spherical scene or new plane scene. For example, we create a spherical scene. So when the currently active window is a scene window, Layer Manager plays as a tool for managing all layers in the scene. And layers in scene have three major types: screen layer, general layer, and terrain layers. Screen layers: only one screen layer can be contained in a scene, but several image objects can be added into the screen layer, and all objects added to the screen layer will be displayed on the globe in the scene. Since image objects in the screen layer are placed on the screen at prescribed positions and are not georeferenced to the scene coordinate system, they will remain stationary when operations such as rotate, tilt, zoom in, zoom out, etc. are performed on the globe. Therefore, you can add what you want to display as static contents into the screen layer. For instance, you may want to display a logo or some descriptive information on the screen as static contents. Then you can add these contents in supported image format into the screen layer. And a scene can only add one screen layer where you can add several image objects. Right-click and click Add Objects. And then we have the terrain layers. Terrain data in .act format you add to a scene will be organized as terrain layer under the terrain layers node in Layer Manager. And the last one we have general layers. General layers is also called as 3D layers. 2D data including vector datasets, grid datasets, and image dataset, image catch data, model catch data, and camel or KMZ data added to scene will be organized in 3D layers. According to the type of data connected to a 3D layers, 3D layers type include dataset-based 3D layer, the type of a 3D layer generated from adding a 2D dataset to a scene, and a factor layers, the type of 3D layer generated from adding a 2D factor dataset to a scene. We have image layers, the type of 3D layer generated from adding a 2D image dataset to a scene. We have grid layer, the type of a 3D layer generated from adding a 2D grid dataset to a scene. And we have model couch layer, the type of 3D layer generated from adding model couch data in .sep format to a scene. We have image couch layer, the type of 3D layer generated from adding image couch data either in .sci3d or SIT format to a scene. And the last one, we have the camel layer, the type of a 3D layer generated from adding camel data either in camel or CAMZ format to a scene. Now, after the explanation about layer manager for a scenes node, we will continue to create exercise data based on the 3D data. The first one, we will create a 3D vector based on 2D vector dataset. Can close this one first. So we have data sources need to be open. Right click on the data source and click open file data source. Now we have in exercise 1, open this digitizations.udb. There are some datasets, an image that already been georeferenced, a reference point for georeferencing, and this is what we will create for this image dataset. This is a vector dataset based on this image. Maybe we can delete this one first so it remains as a original digitizations dataset. So currently we have this image georeference. Right click or double click in this image dataset. So this is the image in the map windows, and we will digitize this image. So you can see on this image, we will do a vectorization of this area using a vector dataset. So we need to create a 2D vector dataset inside this digitization data source. Right click and click new dataset. We will create a type of region, and the dataset name is building. Click OK, and we need to set the coordinate system properties. Right click at the building, click properties, and we have this one coordinate. And we can copy the coordinate system from the existing dataset inside the digitization data source. Click copy, and then we choose the data source is digitization, then the data set is New Haven 1894 adjust. Click OK. Now the coordinate system has been changed into the same coordinate system with New Haven 1984 adjust. And then we add this data set into the map window, And now the layer manager already lists the building dataset. And we need to turn on this editing tools. And then we will do the factorized region. We will do the automatic factorizations. But we need to change the settings here first. And we can set the color tolerance as 50 for example. Click OK. We can zoom in. Can zoom in here. And then we will do factors region and click on the image like this. So it will digitize the objects inside this image within the same color tolerance. Like this. We don't need to digitize them all. Just few samples like this. Okay, so you can see here we have some objects. We have a 2D vector data of this image data set. So what we do next, we want this 2D vector data set become a 3D vector data set. How to achieve that? We need to set a attribute field as a height for this 2D vector data set. So currently, the attribute table for this data set, we can see the attribute tables. Right click and choose browse attribute table, and this is the default attribute table for this data set. There's no height, and we want to add this new attribute field as height. Right click and choose properties. There's an attribute table bar, and we add new one, and we change the name as like height, and the type is long is okay. Then click apply, and there will be a height, right? Height field in this data set, and we need to enter the value of each column in this attribute field. We can update all using right click on the height field and click update field, and we can choose assign to all, and the operation value is the number of the height, for example 100. Then click apply, and there will be 100 number value of the height on each column, and we can change several values of this. Okay, so now we already create a new field as height as parameters for creating a 3D vector based on the 2D vector data sets. So what we do next, we can close or we can save this as map. Okay, so now we need to open this data into a scene window. How to do that? We can choose the data that we want to open at the window. We can directly open more than one data set in one click. Just I will open this new Haven 1984 adjust and building. right click and choose the Add to New Spherical Scene. So, and then we need to zoom to layer this, and this is actually this is dark, and we can turn off this sun effect. Okay, like that. And now it's already a 3D. It's already a 3D in 3D scene, but you still can see that. You can see here the data is still into the visualization, right? We need to set the styles of this data so that this data can change into the 3D visualizations. Click on the Styles tab and choose Extension, and the altitude mode we had many altitude mode here. According to the data sources, there are a ground data and underground data. For ground data, we have the altitude mode as like climb to ground, and when we use the climb to ground, the elevation height of 3D data will be ignored completely. Each 3D objects attached to the terrain surface according to the latitude and longitude and terrain fluctuations. And shown as the following figure, when used the climb to ground, the elevation height information of region object is ignored, and the region objects attached to the terrain surface according to coordinates of latitude and longitude fluctuations. And we have also absolute altitude. The absolute altitude mode is the height relative to the sea level. This mode ignores the terrain real altitude when know the exact altitude. It's useful, and as shown in this mode, the border nodes of a region object in scenes are based on the sea level. And we have also relative to ground. The altitude in relative to ground mode is the height relative to the terrain surface in latitude and longitude coordinate values. And we have also climb to objects. When climb to object is employed, vector data will climb to a terrain, as shown below. Like in this climb to object, the elevation information will be ignored and climb to the terrain model data if climb to object model has been employed. Climb to object altitude mode often applies to object photographic models in a scene. And the last one, we have the modified terrain. Modified terrain mode is often used to a terrain in vector region area. If the model and terrain do not match well, you can flatten or raise the terrain to make the terrain and model match. While employing the modified object model, the altitude of the point position of the vector region will raise up or down according to bottom altitude at the vector of the vector region. And for this exercise, we will create a relative to ground altitude mode, and we need to set the extensions as the height field. So now you can see the 2D vector data. We already extract the height of the 2D vector data. Can adjust the view. This can adjust the view with this button too. So now we already have the 3D vector data set. But this view is not nice. We should create textures. We should create textures for this data set. We can choose this extension and click the texture settings, and we can set the texture for side textures and also top textures. We can choose the texture file at the side, click select file, and there's a texture files. Like we can use any format. Any image format like JPG, PNG, JPG, or any others. Now we can add any kind of image, type of image. For example, we will choose this one, site file.jpg, and it will automatically update on the scene window. And for top texture, we can select this one, and now you can see that this building is already having textures for side and also top. And if you want to change the colors for this 3D vector dataset, we need to go to the layer manager, right click, and change the layer style settings. You can choose like this one. For example, we choose another colors and click apply. Okay. This. So the color will be like automatically changed when we choose another colors on layer style settings. And if we want to save this scene, so later on when we open the project file, we can still see the scene and we don't need to click the view again, and we can open the exact view of this scene window. Right click on the scene and click save scene. Now we can input a scene name and click OK, and it will be saved as a scene note under the scenes as this one as a child node under the scenes node. So we can close this one, and if we want to open it again, the view remains the same. Like this. Okay, so that's all for the exercise 1 of creating a 3D vector dataset based on the 2D vector dataset. We will move to another section or another exercise for the 3D data processing. We can close this workspace or we can save this workspace. I will close this workspace first. Okay, now we will open a 3D object photogrammetry data, and we will do some 3D analysis based on the object photography data. Okay, I was saving this exercise as a workspace, so we need to open the workspace, the existing workspace. Right click and open file workspace, and there's in the exercise 3 we have the osgb.smwu. So this is actually not the default UDB, so we need to delete this one first. Okay. Okay, and this is the scenes. We have already saved the scenes, 2 scenes for this workspace. The first one is OSGB, so we can directly open this OSGB file. Right click to zoom to layer. So this is the object photogrammetry data which already opened in SuperMap iDesktop. you may have a question how to import this data into the 3D data set in the SuperMap iDesktop. So for object background of the data, we cannot import directly using the import button in this one in the import datasets. But we need to create a configuration file. This one, 3D data. We need to create a configuration file. This one, create a configuration file. And we need to import to choose the source data. For example, we have the OSGB data. There will be a source data contains of file image of this object or of this model, and we can choose the source data, and we can save the result as a configuration file. And if we do have a projection for this data, we can set the projection settings, or we can set it as planar. And we can click OK to create a configuration file. After that, we can open the config file in this general layers or the terrain layers, because it will create a patch for this data set. And we can add the OSGB patch layers to import these models of object photogrammetry data. So after we import the data, it will look like this. We can adjust the view of 3D object photogrammetry data. And for this example, I will show you how we do the count to objects output mode. So actually we have this polygons. This polygons is corresponding with this object photogrammetry data. And we want to drag this data into the scene window, and actually the data is below the object photogrammetry modules. And if we change this styles of the output mode as frame, so now it's a frame to ground. We need to frame to ground, and if we want to frame to objects of the object photogrammetry data, we choose the frame to objects. Okay, so now that's already framed to objects. That's actually used for example, object photogrammetry data is a continuous surface. We cannot do such a query for each object inside the object photogrammetry data, such as building, roads, or any other objects. So this way can help us to query or to click each building or each object inside the object photogrammetry data. We can integrate the attributes information with the object photogrammetry data, and we can set the transparency of the style layer. We can set this one. We can set the properties too. And after that, we can do query to see the attributes information. of this building, like the user ID, name, or any other properties of the field. That for this analysis, we want to do some 3D analysis based on this data. So in SuperMap, we have many kinds of 3D analysis, and we have in the 3D analysis menu bar, which will be active when we open the 3D dataset. So menu bar in the ribbon menu in the SuperMap iDesktop is a context sensitive. For example, we have the dynamic feature analysis and also feature analysis. Okay, we will start for a feature analysis. So a feature analysis is a process of extracting areas that can be seen from one or more observer points with relative altitudes, given an observation distance and directions, and on a grid data surface, and outputting the analysis result as a grid data set. So we will do a feature analysis. Click on this tool. Specify the observer points. They can be added by clicking the mouse. And there will be an area here. The green area is the area that can be seen. Okay, the green area is the area that can be seen from that observer point, from that point of view. But the red colors is the area that cannot be seen from the observer point or the point of view for the observer. And the dynamic feature analysis is a static analysis for doing this visualization or this analysis. And actually we have the dynamic feature analysis, so it will be dynamically move from one place to another place. And dynamic feature analysis is used to identify the features that you can see or cannot see from a certain horizontal and vertical angle of view as you walk along a route. And the animation is used to show intuitively the coverage of sight and distinguish the visible and invisible space with different colors. For example, we create dynamic view shots, and then we choose the observer line, draw a line to proceed dynamic view shot, and click and right click to finish the analysis. And there will be an animation of this dynamic view shot analysis, like this. And you can see there is a man walking along the route, and this man shows up the point of view of the observer. Okay, we can play this analysis again. So you can see this one, the green colors is the area that can be seen by this man, and the red colors the area that cannot be seen by this man. And we can set the visible distance, horizontal perspective, and also vertical perspective, and also the row, which is also custom row. And this one is now we can change into car, or we can change into female, or we can change into a plane. Of our plane, it will be upper like this, and we can also set the angle and set the total distance, total time, and also speed of the analysis. We can see if we adjust the third perspective, it will be changed to like this is narrower like this. Yes, okay, like this. Change the parameters. Can change also the time for doing the analysis. And click. And we can see the plane is moving time to time from one place to another place along the route that we already did before. So that's the dynamic view shape. And we have the profiling analysis. Profile shows the change of elevations along the line or the sections, and the research of the profile, terrain, geology, and hydrology features of the certain sections, including the landform, outline, absolute and relative elevation, geologic structures, slope features, surface cutting range, erosion, etc., is very useful for the estimating of the visibility for building railway or the difficult for building road. It can also provide foundation for calculating earth volume. Perform the profile analysis for the raster space. We can get the profile line and also provide pictures. And the profile analysis functionality in SuperMap is used to create the profile along a given line and then get the sampling points. And we can click this profile analysis, and we need to draw a cut line, start point, and also a end point, and it will automatically create profile information, and we can drag on the image, and we can see the altitude, longitude is changing, and the altitude also changing. And this is the sections of the profile for this line that we already drew before. And we can also save this information as an image. And we also have the feasibility analysis here. Feasibility analysis is often used in 3D analysis, and the function is used to determine whether certain locations in a 3D scene are feasible to the observer location. And in feasibility analysis, there are observer points to be observed, and there can be more than one point to be observed. The result of the analysis are lines of feasibility, and the feasible part is green and the red part is in red. So, for example, I want to see the feasibility analysis from this point of view of the building. We can draw a viewpoint, and there is like this one, this point. This point can be seen, so because there is a green color, always a green color into this point, then it means that this point can be seen. But if we do choose this point, we only can see this point until this point, like this. So you can see the difference, right, between dynamic view shape analysis, and also feasibility analysis. So for this exercise, we only want to show you about our 3D analysis and how to import and upload photogrammetry data into SuperMap iDesktop. So next we will do this one. We will close this workspace, and we will open the 3D model data based on modeling using the 3D Max, and that's a city model. And we will do some analysis, another analysis based on this data. Okay. Next step, we will open the file Workspace, and we will open the exercise 2 as a city building modeling using a 3D Max software. This is the .xxwu extension data. So now it's already being opened, and we have some scenes saved at this workspace. We click CBD scene, and there will be a scene display for this city model. So for this exercise, we will do some analysis that can be applied for this scene, and the analysis is actually a sunlight analysis. Sunlight analysis is used to calculate the duration of sunlight in a period of time within an extent defined by longitude and also latitude. And the analysis result is a collection of sampling points having values showing the ratio of sunlight duration to the specified time span. And for the sunlight analysis, we can draw a regions to proceed the analysis, and right click if we finish drawing the region or the polygons, and there will be sampling points showing the value of the ratio height like this, and we can change the parameters for the sampling point, such as like the minimum height. Right now the minimum height is 1 meters, and we can set the minimum height as like 0 from the bottom level, and there will be a new line displayed for the height of 0. Okay, like that. That's the new line appear on the windows. And we can also set the maximum height sampling distance. So now the sampling distance is 5 meters from one sampling point to another sampling point. And we can also set the sampling time. And we can also see the information of each sampling point, like the coordinates x, y, z, and the daylighting ratio. And you can see the daylighting ratio from the bottom level is lower than the upper level. And next, we will create a flying route. So we will delete this sunlight analysis. We have the flying manager and the flying route group on the flight tabs organize operations related to the flying routes and stops. And you can create, convert, and delete 3D flying routes and manage its stops. So we have actually a fly routes saved as the FDF data extensions. We can open it. Okay, and there will be a list of the stops from the flying routes, and the stops is can be created by using the camera view or the click, or the stops by click, and we can play the animations of the of the whole project inside of the city modeling. We can adjust the view, and also we can adjust the height and the angle of the camera. And there will be a display from one stop to another stops based on the list of the stop that we already created before. We can also adjust the speed and also the durations of the analysis. Okay, you may have a question how to create a route using our own stops. So we can create a new route, click the new route, and we can create a new line route. And also we can adjust the view by using a camera settings, also adding the clicking by stops. Adding stop by clicking, sorry. For example, this is the camera view. We can click for the first stop. And then we will choose a different stops by using the click button. And there will be two stops listed on the list. And we can set the speed and also duration. We can play it and it will move from one point to another point. And you can see the duration of this analysis is 22 seconds per point per stops. So it just too slow. So we can directly change the speed, or we can choose the duration. So we need to choose whether we want to change the duration or whether we want to change the speed. And we can also save the result for the flying routes as the .fpf. And we can also change the parameter settings here on the tab on the menu bar. So now we can see that we will visualize the route with the line colors and also the stops. And we have like another analysis, that's a Skyline Analysis. The Skyline Analysis, the function of the Skyline Analysis is to generate the boundary between the building tops and the sky from the observer points. So for the Skyline Analysis, actually we need to do the analysis, and then you can see the blue colors. There is a blue boundary from between the building tops and also the skyline. This is actually used for if we want to see the clear area for the plane to depart or to landing from the airport. We need to see the Skyline Analysis because it's just a view of the plane from the point of view of the plane. So that's how the Skyline Analysis works. Okay, so let's move to another exercise. We will open building information modeling data, we have plugin for SuperMap plugin for some BIM data, BIM software like Revit, Katia, Autodesk 3D, and also Bentley and IFC for map. And this plugin will export the file data into UDP structure format data. We just need to install the plugin in that software. So now we will open the data source that we already export the Revit data from the plugin of SuperMap. Click Open Data Source. Choose the data source.gdb. Click Open, and the plugin will convert or will export all of the information inside the building information modeling, like wall, floor, window, rails, or ramps or railings, and we can open those objects in one click using Add to Numerical Scene. And we need to add as the layer manager and zoom to layer, and we can see this one. This is the view. We can adjust the view, and this is the building. Actually, this is the building information modeling, and we can see all of the information inside this bin. For example, we want to see the windows, we want to see the wall. For each objects, we can see the information or the attributes for each object. So what we do with the building information modeling in this exercise, we will do some analysis, the SQL Query analysis based on this data. The SQL Query is inside in the analysis menu bar, and we choose the SQL Query here. Click on that SQL Query. And choose the SQL Query button. For example, we want to know which windows is located in the 8th floor of the building. So first one, we need to select the dataset windows, and we need to choose the attributes. This is in Chinese, but it's stated that the level of the height of the building, and we can get the unique value of this field, and where select the field attributes, and where the field attributes is equal to 8th floor. And for the result, we can browse in attribute, browse in map, or highlight in scene, and we can also save the result. And for this exercise, I just want to save this result, and that's the result, the query result 3, and open it into numerical scene. So we can see that there is a windows only in 8th floor, and yeah, like this. And we can also see the information of each object in the window, like the user ID, the name, or the floor located at. We can also select the attributes, or we can also browse the attribute tables for this model or for these objects. That's actually all for the building information modeling data processing example for the query, doing the query or doing the analysis. And the next one, we will show you how to create, if you want to publish a 3D surface in SuperMap iServer. The first one, you need to generate a scene cache, and you need to put the cache name, and also choose the cache path, and also you need to change the catch type for this BIM. Maybe it's only applied for 3D tiles, but for raster and also for any 3D vectors, there are different different catch type that you can choose. And then you can generate the catch, and after you generate the catch, you need to open the new vertical scene and add this catch into the general layers or into the terrain layers, or yeah, it depends on the data that you are creating catch from. That's all for the building information modeling exercise. And the last one, I will show you a raster data. This is the DM data, and we will do some analysis, another 3D analysis based on this data. This is the data smartcity.xxwu, and we have the scenes and also the data source, and we will choose the scenes data smart city, or we can choose the data source. For example, we will open this DM data, and we can open it as terrain and also as image, and click OK. And after that, we zoom to layers, and we can like turn off the sun effect here, and you can see there's a DM or the terrain data for the area, and also some building heights. You can see the difference between the colors. We classify the height by the colors, and this is the DM classification using colors. But we can also add the textures for this terrain using the orthophoto or the image. So this one we already overlay the textures and also the TDM data. So after that, we want to do some analysis based on this data, such as like flood analysis. This flood analysis is used to simulate the flooding process over duration of time with the specified speed and also within the maximum and minimum elevations. And it is applicable for terrain and also DM data. We need to create a polygons or draw a polygons and right click, and we need to set the maximum and also the minimum height, because this analysis will apply from the minimum and until the maximum height we set. And also we have the slope and aspect analysis. This slope analysis is used to calculate the slope of each pixel in grid data set, usually use the DM data. And the larger the slope value is, the abrupter the terrain, and the smaller the slope value is, the flatter the terrain is. Okay, the pixel value is the altitude value of this point DM data, and the slope of this point is calculated by the altitude. The slope is the average of every pixel plane in SuperMap, and SuperMap provides 3 slopes format in degree, radian, and also percentage. And next I will show you how we do the export plugin for Revit. I don't give you the introduction how to install the plugin. Maybe you can contact SuperMap staffs to get the plugin first, and then we can open the project file here. Corporate office building information modeling. Can click. So this is the the project file, and we have the add-ins here. SuperMap exporter, SuperMap export for Revit. Click on the button, and then it will display a prompt, a windows that needs to be selected. So we need to change some parameters like a coordinate system. We need to import the coordinate system or input the center point using the longitude, latitude, and also the height, or using the planar coordinate system, and we can save it in the path and give the name of the UDB. And we can also export the LOD, and we can generate, or we can click OK, and after that the UDB will be appeared and in the path locations and can be imported in SuperMap. So I think that's all for the training sessions for the 3D data processing in SuperMap iDesktop. Hope you can catch some information or knowledge based on this training. Thank you for the participation and your time. See you at the next training.